Good morning. We're going to look at solving the series of polynomials. Process is not difficult. It is long and tedious. So a few of the results we're going to need. Remainder theorem. If you divide a polynomial by x minus k, its remainder is f of k. This allows us to quickly check whether a real number is a zero or not, simply by dividing it by x minus that number. Next up, we have the factor theorem. K is a zero of f of x if and only if x minus k is a factor of f of x. This is kind of a result of the remainder theorem. This is what will allow us to factor a polynomial. The next result will allow us to determine the form of any rational zeros we may have. It's called the rational zero theorem. Given a polynomial, leading coefficient a sub n, constant term a naught. As long as those are all integer coefficients, every rational zero of our polynomial will have the form of p over q, where p is a factor of your constant a naught and q is a factor of your leading coefficient a sub n. This result allows us to list out all of our possible rational zeros to check. And generally, it is a good starting point. Fundamental theorem of algebra, probably the most important consequence of algebra, is going to tell us how many zeros we have. Consider a polynomial of degree greater than 0, right, degree n. F of x has at least one complex zero. Said another way, I have no idea what that a in there is supposed to be for. Oh, right. Given a polynomial of degree n greater than 0, some non-zero real number a, f of x has exactly n linear factors. So you can write it as a times x minus c1 times x minus c2 times x minus c3 up through times x minus cn, where each of your ci's is a complex number. what this says is that f of x has exactly n roots, or n zeros, if you account for multiplicities. So if you're given a polynomial with degree 10, you're going to have 10 zeros, accounting for multiplicities. This does include the complex numbers, not the real numbers. The complex conjugate theorem is another nice result. Complex zeros occur in pairs. So if z is a zero, a complex zero of a polynomial, so is its conjugate. And so if a plus bi is a zero, so is a minus bi. So it says all of your complex zeros occur in pairs, so you can't have an odd number of complex zeros. Last one, we'll be using Descartes' rule of signs. This is going to tell us the number of possible positive and negative zeros we have. And when we talk about positive and negative, we only refer to real numbers. Complex numbers don't fall into that category. So you consider the polynomial with real coefficients. Number of positive real zeros is either equal to the number of sign changes that occur in f of x, or less than this by an even number. Number of negative real zeros is either the number of sign changes in f of negative x, or is less than this by an even number. And we'll be using all of these to determine zeros of any polynomial function. So let's start off with the simple cubic. The degree of this polynomial is 3. So we're going to have 3 zeros. Where notice it's saying find all of the zeros. So they also want the complex. So we know we have 3 of them. Here's the general strategy. Start by listing out the possible rationals. So you need to look at your constant, 24, well, negative 24, but just look at 24. List out its factors. So what are the factors of 24?
1 and 24.
Those are 2 of them. They're not the only ones.
2 and 12.
2 and 12.
6 and 4.
4 and 6.
8 and 3.
3 and 8. And that's half of them. You also have their negatives. That's why I say ignore the fact that it's a negative 24. What is the leading coefficient?
0.
1. Oh, that's really nice. It only has one factor itself. In that case, since the leading coefficient is 1, your possible rational zeros are just all the factors of 24. It's not saying they're all zeros. It's just saying that if you have rational zeros, it's going to be one of those. Next up, determine how many positive and negative zeros you can have. So we look at f of x, and what we do is we count the number of sign changes. So it's positive, that's not a sign change. Negative, there's a sign change. There's 1. Negative, that's not a sign change. You have one real zero. You have one positive zero. For the negative zeros, you want f of negative x. Just replace x with negative x. All of your odd powers will switch sign. Even powers stay the same.
Wait, why you switch the sign?
Because I want f of negative x to find the negative zeros.
What about 3x squared?
What's negative 1 squared?
Okay.
So the even powers will not change sign when you replace it with negative x. Only your odd powers are going to be changing sign. Now you count the sign changes in here. Negative, it's positive, there's a sign change. Stays positive, to negative, there's a sign change.
Why 3x squared? It doesn't change the sign again.
Negative 1 squared is what?
Oh, okay.
But remember, the rule said, or less an even number. What's 2 minus 2?
0.
Reason we ignore it with 1, what's 1 minus 2? Can you have negative 1, 0?
No. Wait, so how do you get 0 again?
2 minus 2. It's less an even number. Right? So we could have 2 negative zeros, or we could have no negative zeros. That's what that's saying. But we are guaranteed to have 1 positive, which is nice. Now use all of this along with fundamental theorem of algebra to list out our possibilities. I'm going to make a table. Positive reals, negative reals, and complex. One combination we can have, one positive, two negatives, which means we'd have no complex, because that already accounts for our 3. We could also have one positive, no negatives, which means we'd have to have 2 complex to account for the 3. And that does square away with the complex conjugate theorem. Right? Number of complex zeros has to be even, because they occur in pairs. So when we find all of the zeros, it's got to be one of those 2 possibilities. One positive, 2 negatives, or one positive and 2 complex. Now comes the worst part. We have to find one of the zeros. And we hope that it does have rational zeros. Because if it doesn't, we cry. We have to test each of those rational zeros we just listed out to see which one's a 0. We do that using the remainder theorem. Remember, remainder theorem said, if you divide your polynomial by x minus k, your remainder is f of k. So divide that polynomial, x minus 1, see if you get a 0 remainder. X plus 1, see if you get a 0 remainder. Right, so you want a 0 remainder, because that's going to tell you that's a 0. Now I'm going to make things a little easier. I know that I have to have a positive 0. I'm just going to check the positive rationals. I'm going to ignore the negatives, because we may not have a negative. I'm going to list out the coefficients. Let's start with 1. One comes down, times 1 is 1, plus 3 is 4. Times 1 is 4, minus 10 is negative 6. Times 1 is negative 6, minus 24 is negative 30. That's not a 0. And how you go about checking these, the order doesn't matter. I try to be systematic.
Wait, so to find the zeros, you have to go up the line to like 1, 2, 3, 4, 6, 8, 12, and 24 until you get a 0.
Use synthetic division with those numbers until you get a remainder of 0, because then that tells you that's going to be a 0. So I'll try 2 next.
Why did you put like only 1, 3, minus 10, minus 24, and not?
Those are the coefficients.
Oh.
So I'm using synthetic division here. I'm doing a modified synthetic, so I don't have to list it out each time. I can just use one constant table. 1 comes down, 1 times 2 is 2, plus 3 is 5, times 2 is 10, minus 10 is 0. That's not going to give me a 0. Let's try 3. 1 times 3 is 3, plus 3 is 6, times 3 is 18, minus 10 is 8, times 3 is 24, minus 24 is 0. Yay. 3 is a 0, which means x minus 3 is a factor. Rewrite f of x.
F of x plus 3.
Do it down here. I'm kind of out of room. You know x minus 3 is a factor. When you factor it out, what are you left with? X squared plus 6x plus 8. So the idea is you want to keep repeating this process until you get a quadratic factor. Right? So until you reduce it down to a quadratic. Because quadratics you know how to solve. We have a quadratic. Can we factor that quadratic?
No.
Factors of 8 when added give you 6.
Oh, yeah.
That can be factored. X plus 2 times x plus 4. You've completely factored your polynomial now. Those are all of your zeros. 3, negative 2, negative 4. There's our solution set.
So the rule, it has to be minus 3. Like why don't you just put x plus 3, x minus 2, x minus 3? Like at the end.
Because remember, it's x minus k.
Okay. And then what about the x plus 2 plus?
So that would just be x minus negative 2, right? And then just make sure that that does satisfy one of the possibilities we listed, which it does. That's 1 positive, 2 negatives. And that is the general process. Not a particularly difficult process, but it is tedious. Especially if you get extremely unlucky in which numbers you're checking.
So realistically, like if you didn't understand how to do like the whole plus zeros, minus zeros, that thing, you could just check all the factors and then you're still getting. Okay.
That just makes it easier.
Yeah, because I don't understand how like the whole plus zeros and minus zeros thing. I don't get that.
We have some more, so let's see if it helps click. Factors of 18.
One, 2, 3, 6, 9, 18.
Factors of 3.
1, 3.
So we're going to start off by listing out all the factors of 18. Remember, it's always positive or negative. That takes care of factors of 18 divided by 1, which I'm going to try to stay systematic. So we could also have plus or minus a third, plus or minus 2/3. What's 3 over 3?
1.
It's already listed. What's 6 over 3? It's already listed. What's 9 over 3?
3.
It's already listed. What's 18 over 3?
6.
That's already listed. So no need to relist them. Those would be all of our possible rational zeros.
And why those two or the others? The ones that aren't listed?
No, all of these are possible zeros,
Oh, okay.
possible rational
Yeah,
zeros.
yeah,
Right, so if there's a rational zero, it's going to be one of these. That's up there.
yeah. Why you divided them by 3?
What are the factors of 3?
Oh, that's right. Oh, so it's not everything.
So it's always of the form P over Q. P is a factor of your constant term. Q is a factor of your leading coefficient. So that first line takes care of when you're considering the factor of 3 as 1. That second line is going to be when it's now 3. Determine how many positive zeros we're going to have. So look in f of x and count your sign changes. Positive to positive, that's not a sign change, right? To positive, still not changing signs. To negative, there's a sign change. Back to negative, that's not a sign change. You have one sign change, right? That means you have one positive zero.
I understand that. It's just the little chart you made. I didn't understand that really, like switching. Because I know, like now, like where you can do a negative x.
So replace x with negative x. Typically what I do is I just write what the signs are going to be. Right? Sign doesn't change for evens. Sign does change for odds. I kind of just write what the signs are. Right, so positive to negative, to positive, to positive, to negative. 3 sign changes, so our negative zeros. 3 less an even number.
What or 1?
3 minus 2. Right, it's not the number of sign changes. It's the number of sign changes or that less an even number. Right, so 3 minus 2 is 1.
So is it always going to 2.
Or 4, 6, 8. The idea is you keep going down until you're going to get a negative, right? So what's 3 minus 4?
3 minus 4 is -1.
Which doesn't make sense. You can't have a negative number of zeros.
So you would do like, say you had like 5, then you would do -4.
Yeah, so then you'd have 5, 3, or 1. Right, because it'd be 5 minus 2 and then 5 minus 4. Right, listing out our possibilities. So we know we're going to have one positive 0. We could have 3 negative zeros. What's the degree of our polynomial?
4.
So we have to have 4 zeros total. 1 plus 3 is 4. We'd have no complex in this case. But we could also have a negative 0, right? Just a single negative. So 1 positive, 1 negative.
2.
You'd have to have 2 complex. Those are the only possibilities. And again, you just want to make sure that you did everything right. Number of complex zeros are even, as they have to be. So when we find our solution, it's got to be one of these two. Now let's start checking. So here's the question. Do I want to go through the list, or do I just want to skip to the one I know is a 0 for the sake of time?
Or just do one that's not, and then the actual one. Get some practice.
I think for the sake of time, I'm just going to skip to one I know is a 0. Yeah, but just realize, again, there's no, you don't have to pick any order, right? You don't have to go 1, 2,
So there,
in order. You can just pick a number. Like if you think 1's a 0, check it. So if you think 1's a 0, pick it, check it. If you think 9's a 0, check it and see what happens.
Is there any like trick to that? Like, so you really just gotta waste your time like on the test?
Other than looking at a graph. But even that's not always 100% accurate.
So this question could take up a lot of time on the test.
But that's also why a question like this would be worth a lot of points. And because how long it's going to take you. So let's list those out. I'm going to check -2. I know that I have to have 1 positive and 1 negative. Three times -2, -6, plus 16 is 10. Times -2, it's -20, plus 20 is 0, which means that -9 is going to drop down. -9 times -2 is 18. Right, minus 18 is 0. There's a 0. That means x plus 2 is a factor. And that's what we're left with when we factor it out. 3x cubed plus 10x squared minus 9. So now the idea is you take that term, let's call that like f sub 1. Repeat that process on f1. So we do the exact same thing, but now on f1. Factors of 9.
1, 9, 3, 9.
And factors of 3.
1.
Now, save yourself some time. I don't need to worry about doing, actually I could. Could do Descartes' rule of signs. Going to get 1 positive, 2 or 0 negatives. You don't really need to because we already did it. So honestly, I just stopped there. But check the numbers you already checked. Right, so I checked 1, -1, and 2. I actually checked 1, -1, and 2 in my notes prior to -2. None of those were zeros, which is why I made it all the way down to -2. Well, if they weren't zeros of the original polynomial, can they be a 0 here?
No.
Well, that's fine because 2 is not even listed as a possible here.
So it's 3 or 9.
But 1 and -1 are listed. But we just determined they can't be. So don't check them again. Oh, for Pete's sake, you know I'm in class. So that just saves you some time. There's no point checking 1 and -1. They can't be zeros. You already checked them. Right, so now it's either going to be plus -3, plus -9, or plus -1/3 as the possible rationals. So we have to check them. Okay, so let's say we check check 3, we find out that 3 is not a 0. Check 9, we find out that 9 is not a 0.
1/3.
We check a third, we find out that 1/3 is not a 0.
So then it's just the regular, the equation at the top. Oh, then you have to start doing negative?
Yeah,
So I check out.
Wait, so we have to do all of those listed positive, and then if none of them are zeros, then we have to do all of them negative?
Right, because remember, we said we could have 3 negatives.
So what if like all, like what if we had like 10 of those things like right there and none of the positives?
That's why I said, depending on how lucky you get, this could take a while.
There won't be a question in the exam with that many like possibilities, right? That doesn't even make sense.
Could be. Again, you have to keep in mind that it's going to be weighted heavily.
It's a 90-minute exam, right?
100.
100-minute exam. Okay. How many questions?
Well, I'm not going this one. I don't remember.
Okay.
No, but it could be that you only get 3 questions and one like this really nasty long one that's worth 70 points or something.
Yeah, I mean, you should make it like that so that at least you can pass it and get it right.
And that would be really evil and say it's all or nothing.
That's
It's
what,
no partial credit.
That's what.
or you could give an equation with like 20 of those.
I could give you
That's
a
the
high
exam.
degree.
That's the full
But then I have to write a solution, that's not going to happen. 3 times -3, not -9, plus 10 is 1, times -3, -3 plus 0, -3 times -3 is 9, and plus -9 is 0. -3 is also a 0. We already have the x plus 2. But now we notice that we can factor f1. X plus 3 was a factor. And what's left? 3x squared plus x minus 3. We got it down to a quadratic. So we're done with this algorithm. Can that quadratic be factored?
No.
Not the way you were taught, no. It can actually be factored. Has to be.
Using the box method.
Even that's not going to work. Right, we have already listed 2 negative real zeros, right? Which means we have to have 3 of them. 2 is not a possibility. It's either 3 or 1. Since we already found 2, there has to be 3. Which means we have to have 1 positive real and no complex. So when we solve that quadratic, we're going to get real solutions. Since you can't factor it using known methods, there's only one way to proceed. What is that formula?
That one? Oh, the quadratic?
Quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. B is 1. A is 3. C is -3. Three times -3 is -9. 4 times -9 is -36. 1 minus -36.
Square root of that is 6 points.
We don't worry about the decimal approximation. We leave it as root 37. Root 37 is not rational,
Yeah.
so you just leave it. Solution. We have -3, we have -2. Again, the order in which you write them doesn't matter. I like to write them in ascending order. Those are the zeros.
And that last one is the one positive.
Yes. But you can figure out positive or negative just by doing approximations. Right, so root 37 is larger than 6, slightly larger, which means when you subtract 1, it's going to be slightly larger than 5, positive. And then you get positive over positive is positive. So that's how I know it's positive. It's going to be slightly larger than 5/6. Now versus, obviously, root 37, again, slightly larger than 6. So you have -1 minus that is negative. I'm already done. In fact, that would be slightly, less than -7/6? And so there's the 3 negatives, 1 positive, and we're done. So that's the goal of this algorithm, is to do it until you get a quadratic factor, because you know how to solve the quadratic. Quadratic formula is the easiest way. That always works. Rational zeros. Factors of 18. Oh, we did them already, right?
Yeah.
Factors of 4.
1/4. Oh, 1 and 4, and 2 and 2.
1, 2, and 4. All right, well, let's just now work with 2. Divide each of those by 2.
1/2. 1 over 3/2. 2.
6 over 2.
3 and
So we don't have to worry about that.
9/2.
And 18 over 2. 9. We already have it. Now go back to that first line. Divide everything by 4.
Oh, no.
Quarter. 2 over 4 is a half. Already have it. 3 over 4. What's 6 over 4? Already have it. 9 over 4 doesn't simplify. And what is 18 over 4?
Where we have it.
It's 9 halves. There's all of your possible rational zeros.
So we'd have to check all those.
Oh, you hope you don't have to check every single one. Hope that you get lucky enough where you pick some and you find the zeros you need before you exhaust the list. Number of positive zeros, number of sign changes. Go positive to negative, to negative, to negative, to positive. That's 2 sign changes. So it's either 2 positive or no positives. Positive to positive to negative to positive to positive. So there's either 2 negatives or no negatives. Now to list out possibilities. Start with the case of having 2 positive real zeros. You could get 2 negatives, right? So there'd be no complex. But you could also get no negatives. So you have what? 2 complex?
We have no positives.
Could have no positives, 2 negatives, which means we'd have 2 complex.
Or you could have 0.
Or you could have no negatives, which means you'd have 4 complex. That means all of your solutions would be complex in that case.
So understand like positive zeros and negative zeros, like how there's 2, like how in the Butler equation you can find 2 by rotating back and forth the sign. But like why is it 0 2?
Again, 2 or less than even.
Okay.
So you have to remember that you can also have less than even number. Right, so Descartes never really tells you exactly how many you have unless there's only 1 sign change. If you have, or there's no sign changes. If you have any more than 0 or 1 sign change, it only tells you possibility of number of zeros, not a definitive number. We hope
It's not 4.
that it's not that last case. Because if it is, that requires complex analysis.
I don't think I have that yet.
No, that's a senior level math course. There is a way to do them, actually. There's a way to do this even easier using techniques of complex. It's way easier than this. But again, you won't study that unless you're a math major. So again, if you find out that none of those, well, even if we have one of the other 3 cases, but none of them are rational zeros, you cry. Because you have no way of determining any of your zeros using these techniques. So So let's start by checking. And hope that we find a rational zero. All right, so pick a number. Which one do you want to start with?
1,
1. It's not a zero.
2,
Not a zero.
3, 4.
Not a zero.
4.
Not a zero. Well, 4 can't be that funny.
6.
Not a zero.
9.
Not a zero.
18.
Not a zero.
1 half.
Not a zero.
3 halves.
3 halves is a zero.
So I have to go.
4 times 3 halves is 6, minus 4 is 2, times 3 halves is 3, minus 7 is negative 4, times 3 halves is negative 6, minus 6 is negative 12, times 3 halves is negative 18, plus 18 is 0. All right, now repeat that process. What's the constant?
12.
List out its factors.
1, 2, 3, 4. 12. 6 and 12.
Your leading coefficient is 4, so we have to divide each of those by 2 and 4. Look back at your original list. Oops. 4 and 12 was not in that original list, was it?
No. So 4 and 12 was top.
That means they can't be zeros. So you can immediately eliminate them. Also, remove all the ones you asked me to check before.
Yeah.
You already know they can't be.
So it's just a fraction of them, except 1 half.
Or the negatives, because you only gave me positives.
Yeah, just cross them off.
However, make it easier. We have a positive real zero, which means we have to have another one,
So
right? Because you have to have 2 or none. So just check the positive values, because you know you have to have another one.
3 halves.
3 halves is a 0. Remember, there's no rule that says it can't repeat. Right? So yes, we already checked 3 halves, but we found out it was a 0. It stays in the list.
Quarter.
Because it can occur more than once. That's what a multiplicity is. Looking at the wrong one. 4, 2, negative 4, negative 12. Three halves, once again, is a 0. 4 times 3/2 is 6, plus 2 is 8, times 3/2 is 12, minus 4 is 8, times 3/2 is 12, minus 12 is 0. So we now have x minus 3/2 squared. It occurs more than once.
Or you could just write it out, right?
You could. Is that a quadratic?
Yeah.
So we don't have to worry about that process anymore. Can that quadratic be factored using techniques?
Yes. No.
No, it cannot. Which means you have to use quadratic formula. Negative b plus or minus the square root b squared minus 4ac all over 2 times a. I think what I'm going to do is copy that bit onto another slide. Uh, 4 times 8 is 32. What's 32 times 4?
124. 128. 128. So it'd be 64 minus 128.
128 sounds right, yeah. And then, 64 minus 128 is what?
64.
Negative 64. What's the square root of negative 64?
8. Negative 8? No. It's like what's it called? One of those numbers with the I. A complex? Oh, okay.
8i. So when you simplify, you get negative 1 plus or minus I. There's your solution set. You do not want to list out 3/2 more than once. Right, so you typically never list a 0 out more than once if it occurs multiple times.
What would you be wrong? Like, would you mark this wrong?
I probably wouldn't. I'm trying to determine if it actually be correct mathematically. I don't think mathematically it is correct. Because when you write a set, you don't list an element more than once. Right, but notice this doesn't violate the rule of having exactly 4 zeros. Because it does say you have to account for multiplicities. Since 3/2 occurs twice, that gives you 2 zeros, then your 2 complex is 4. You didn't notice what was an option?
2 positives, 2 complex.
It is an option, right? It's the second one. 2 positives, no negatives, and 2 complex. So what about here?
Just 1. The Q0, what does the Q stand for?
Rationals.
So the rational zeros is 1.
Or
Or
0.
0. Or 1. 1 or 1.
1 or
Infinity.
Negative 1.
Negative infinity.
It's always plus minus.
Oh, yeah, that's right. Plus or minus.
Okay, but look at the sign changes. How many sign changes are there?
0.
Which means you have no positive zeros.
So it's negative 1.
Look at f of negative x. How many sign changes are you going to have?
0.
0. You have no negative zeros either.
Boom. So that.
That means all 4 are complex.
So it's going to be x plus 0 plus 1.
No, 1's not a 0.
X minus 1.
1's not a 0. Negative 1's not a 0. You have no real zeros here.
So it's undefined.
No, it only has complex zeros. But you did way too much work. Isn't that quadratic form?
If you factor it,
Doesn't have to be factored to see that's quadratic form. Replace x squared with z. X to the 4th would be z squared, right?
yeah. So then that's it.
No need to do the algorithm. You already have it down to quadratic. Solve for z. You have to use quadratic formula. Oh, actually, no, you don't. This can be factored. The z plus 1 quantity squared. Now just set that equal to 0 and solve. Z is negative 1, right? But what was z?
X squared.
So what's x?
I.
Plus or minus I. Oh, and since z plus 1 was being squared, that means each of those has a multiplicity of 2. So I occurs twice and negative I occurs twice.
Well, you don't have to write it once, right?
So solution set is negative I and positive I. And let's say we wanted to actually factor this, write it as a product of linear factors. how you would write it. So if you get a polynomial, check to see if you can use techniques previously taught. So your algebra techniques, because that would be the easiest way to go. This can't be done by grouping. So list out your possible rational zeros. Leading coefficient is 1. That makes this nice. What are the factors of 20?
1, 2, 4, 5, so 20.
So those are our possible rationals. I'll list it this way. Positive reals. So how many sign changes do we have in f of x?
One. No, two.
2 of them, right? So we're going to have 2 or no positive zeros. Negative zeros. So let's do this first. When you replace x with negative x, what's the sign of x cubed going to be? So what's the sign of the first term? Negative, right?
Mm-hmm.
Sign changes. Oh, x squared, sign stays the same. X, sign changes. 20, sign stays the same. How many sign changes are there?
1.
So we're guaranteed a negative 0.
And it's, you can't do or 0 because there is, you can't.
Because 0 is not less than 1 by an even. We have 2 positive, we have to have 1 negative, which would leave us with no complex. Or we have no positive, have to have the 1 negative, and we'd have 2 complex. Those are the only 2 possibilities. Now just start checking. Here, since we're guaranteed a negative, you might as well just check the negatives. Right, because you have to have a negative 0. Right, so start checking them. What do you want to start with?
-4.
Not a 0.
-5.
Is a 0. I want to write it here. 1, 2, -31, 20. One times -5, -5 minus 2 is -7, times -5 is 35, minus 31 is 4, times -5 is -20, plus 20 is 0. That means x plus 5 is a factor. And we're left with x squared minus 7x plus 4, which is quadratic. Can that be factored using techniques of algebra?
No.
Nope.
Quadratic.
So we have to use quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c. 4 times 1 times 4 is 16. All over 2 times 1. (49 minus 16). Solutions, negative 5. (7 minus root 33 all over 2). 7 plus root 33 all over 2. There's the zeros. Do we have 1 negative and 2 positives?
Yes.
Yeah. Root 33 is less than 7. So 7 minus a number less than 7 is positive. Now for one I don't have notes for, so this will be blind.
You didn't have what?
I don't have the solution right now for this one.
Oh, okay.
So this one's going to be blind. I'm just going to leave it as rationals. Factors of 6.
1, 3, 6, 2, 3, 6.
Factors of 2.
1 and 2.
So now we have to divide each of those by 2. There's our rational zeros. How many positives are we going to have? So how many sign changes
1,
for an f of x?
1. 2. And then that's going to be two again.
Now this looks similar to one we did. I hope it's not that last case. So let's just start. I have no idea which ones are zeros, so like I said, totally blind. 2 times 1 is 2, minus 3 is negative 1, times 1 is negative 1, minus 7 is negative 8, times 1 is negative 8, minus 8 is negative 16, and I can stop, because I'm not going to get 0 out of that. Sad face. That's not a 0. Bummer.
So you just go back and forth between like the positive and negative?
I'm going to here because I could have both positive and negative. Negative 2 minus 3, negative 5, times negative 1 is 5, minus 7, negative 2, times, negative 6, this is a 0. No, it's not. Times, fine. That's 12. That's not a 0. That makes me sad. So close.
So 2.
This means I have to try 2 now. 4 minus 3 is 1, times 2 minus 7 is negative 5. That's negative 10. No, this isn't going to work. I have a funny feeling. It's going to be a half. Let me just check 2. Negative 2. Negative 4, that's negative 7. 14, that's 7. Negative 14. Yeah. Negative 2 isn't 1 either. Now I'm running out of room. I don't know why. I just have a funny feeling when I get that 1/2 is going to be a 0. 2 times a half is 1, minus 3 is negative 2, minus 1, that's minus 8, minus 4, that's minus 12, minus 6. And 6 is 0.
That's 1.
Hmm?
Well, that's 1.
I know I'm going to have another positive. And then we're left with what? 2x cubed minus 2x squared minus 8x minus 12. Okay, look at the rationals. 1, 2, 3, 4, 6, and 12, a half, 3 halves, and everything else is listed.
So we can cross off 1 and 2.
4 wasn't there before, right? 12 wasn't there before, so they're not going to be there. Right? Plus 1, plus 2 didn't work, so I'm not going to try those again.
So we can cross those off.
I'm not going to completely cross off because of the negative, so maybe what I'll do is I'll just...
I thought we checked the negatives of them.
No. Oh, you're right, I did. You're right. Yeah, so I can cross those off as well.
So it's either 3, 6, another 1/2, or negative 1.
Why do I have a funny feeling it's going to be 1/2 again?
Let's check it.
But I'm not that confident. So the question is, do I want to check 1/2 or do I want to check 3?
Check it again.
This doesn't work, you make it a textbook. Mysteriously fly at you. 2 times a half is 1. That's -1. Oh dear. Minus a half. Oh yeah, this is not gonna work. This is not gonna work.
What about 3 halves?
-8 minus a half. -17 halves, right? Yeah, that's definitely not gonna work. So I'll try 3. 6 minus 2 is 4. That's 12. Minus 8 is 4. Times 3 is 12. I was going to check 3 first, too. Maybe I'll find a mysterious error on your exam. We're left with 2x squared plus 4x plus 4. Oh, that's nice. I'm going to factor out 2, by the way. I think I'm going to write it this way. 2x minus 1 times x minus 3, x squared plus 2x plus 2. Factor out a 2 and distribute it through that first term. Gonna have to use quadratic. -b plus or minus the square root of b squared minus, these are going to give me complex. So that's -8 all over 2. That gives me -1 plus or minus I. Zeros, negative, I'm sorry, not negative. 1/2, 3, -1 minus I, -1 plus I. All the zeros. This process sucks. It'll make you appreciate your calculator all the more when you can use it in calculus.
Hey, you said engineering has to go up to engineering, or Calc 2?
Engineering? Oh no, engineering you go all the way up through differential equations. And you probably want to take some partial differential equations with that as well, depending on what branch of engineering you are. Actually, I think you also need statistics and complex.
Or electrical?
Oh yeah. You would definitely need partial differential equations. But I don't know how the engineering school is going to handle that, so. Let's look at another interesting one. Find all the zeros for x cubed minus 8. Sounds like that elevator is finally replaced and working. All right, so this is given to you in algebra. You typically do what? X cubed equals 8, and just say that x equals 2, right? And be done with it. You're missing 2 zeros. It's cubic, right? That means it's degree 3. You have 3 zeros total. It means the other two have to be complex. Now here's the good news. X cubed minus 8 is a difference of cubes, which can be factored. That is a special factor formula. That's how we factor. X minus 2 times x squared plus 2x plus 4. Which again, you can easily get by realizing that you now have 2 as a 0, meaning x minus 2 is a factor. Do x cubed minus 8 divided by x minus 2. Using synthetic, and you will get 1, 2, 4, and then 0 is your remainder.
So then you gotta do it again?
Well, no, now you're down to quadratic, right?
Then you just put it in a quadratic.
Now it's going to be a quadratic formula. These have to be complex, because if they were real, we would have found the solutions already.
So how would you get down to that quadratic equation? Like say if you didn't know that little thing that you said.
X equals 2 you found as a 0.
Yeah.
Use synthetic division with 2.
Oh, so okay.
Right, so you have as your coefficients 1, 0, 0, negative 8, 2, then use synthetic division. You'll get 1, 2, 4, 0. Two plus or minus root negative 12 over 2, right? Square root of negative 12. It's going to be I, and 12 is what? 3 times 4? Root 4 is 2. Negative 1 plus or minus the square root of 3, I. There's your 2 missing solutions.
Where I low-key forgot how to not I didn't forget, but I remember my past teacher, she said if you had square root of negative 12, right, you break that down into 3 lines coming down under it, so it'd be 3, 4, and negative 1, right? And then the negative 1 would turn into an I. And then what, you just simplify the 4 down to a 2?
So my computer just crashed. That's nice. That's not how I do it. I just look at, I have a square root of negative, so I know it's I. Then I just look at root 12. And it's like what you said, 12 is 3 times 4. And I know 4 is a perfect square. So it'll be 2 root 3. So I ignore the negative right off the bat, because I know that's going to give me complex. So I know I'm going to have an I. At that point, just write it as root 12, which is then standard algebra.
Okay.
That's how I do it. But my computer crashed. I mean, it just completely crashed. this is where we left off. No idea what caused that freeze, but let's hope it doesn't happen again. I think I was basically done. That's the process. Are there any questions on the process? And so I will be honest, I do remember there is one of these on the exam, but it is only real zeros, not complex. You just have to find all the real zeros, and it's really not that terrible. All right, so a few announcements. Number one, I have to leave campus right after this class, so no office hours. My daughter has her 1-year post-op follow-up appointment. I have to leave right away to make it in time. You do have 2 homeworks. All right, one's due Monday, one's due next Wednesday. Second project, work on that. That's about cannons. Cannonballs, it's actually pretty cool. First exam is next class. Make sure you bring with you a pencil or black ink pen. I won't accept any other writing utensil. Make sure that you bring a calculator with you. You can't use mine.
It doesn't matter about the pencil, right? Like number 2 or something.
No, it's not Scantron. And make sure that your calculator is fully charged. Again, you can't use mine if it's not. Also, don't forget the reference sheet. So if you weren't here on Monday, stop by after class to pick up the reference sheet. You can write double-sided on it, anything you want, but it does have to be handwritten, and you can use that for the exam.
And you said one of those that we just did will be on it?
There's going to be finding zeros, but only real zeros. We did all of them in class. The exams, I'm 99.9% certain it only asks for reals.
Okay.
Okay.